Welcome to Lecture 29 of Electrical Circuits 1. In this lecture, the first thing I want to do, as usual, is review what we did last time. So we're going to talk a little bit about the high points of frequency response. I also want to do another frequency response example. I did an RC circuit last time. I'll go over that one again in my review. I also want to do an RL circuit. Now, after we've actually calculated the frequency response, the magnitude response and the phase response, in general, the most common way to present a frequency response is graphically. You plot the magnitude versus frequency and you plot the phase versus frequency. So I'm going to talk a little bit about frequency response plots. Likewise with signals. Frequency response plots show the system's frequency response, what it does to the input and output as a function of frequency. In order to interpret these and what they're doing as a function of frequency, you need to convert your signals into some kind of frequency domain plot. So we'll talk about signal spectra, which is the frequency content of signals, and then we'll plot some signal spectra as well. Finally, I want to talk a little bit about filters, introduce that. Related educational materials are in 2.8.1 and 2.8.2. Now, in the last lecture, we mentioned that systems are characterized in the frequency domain by what is called their frequency response, which I'll call h of j omega. This is a complex number which is a function of omega. I'm emphasizing that it's a complex number by including the j in the argument. The omega in the argument, of course, merely implies that it's a function of frequency. Now, if I do a block diagram form of the system now, I have some input which is going to be represented in phasor form as u of j omega. My inputs and my outputs can now also vary with frequency. We can have multiple frequencies in these. That input is applied to some system which has a frequency response h of j omega, and the output is simply u of j omega times h of j omega. This is a complex number for each value of omega. This is a complex number for each value of omega. At that value of omega, we simply multiply those two complex numbers together to get the associated output at that frequency. So it's a frequency by frequency multiplication of two complex numbers. Now, h of j omega has essentially two parts since it's a complex number. It has a real part and an imaginary part. However, we typically work in polar coordinates with these types of systems. We mentioned earlier that multiplication is more easily done in polar coordinates. So it's typical to represent h of j omega in terms of its magnitude response, which is the magnitude of this complex number as a function of frequency. That simply gives me the ratio of the output amplitude to the input amplitude as a function of frequency. The other thing we need is the phase. So the phase response is the phase of this complex number. That gives me the difference between the output phase and the input phase. It's the phase change as a function of frequency that's introduced by this system. Now let's take a look at this in slightly more detail. My frequency response is h of j omega. It consists of some magnitude response, magnitude of h of j omega, and some phase response, angle of h of j omega. My input phasor, u of j omega, consists also of some magnitude and some phase for each frequency. The output also has a magnitude and a phase as a function of frequency. So to get the output magnitude, we multiply the input magnitude times the magnitude of the frequency response. To get the output phase, we add the phase angle of the input with the phase introduced by the system itself. At this point, I also want to review an example that we did last time. I'll be using this example again throughout the lecture today. We have a simple RC circuit. We have a 0.25 farad capacitor and a 2 ohm resistor. Our output is measured as the voltage across the capacitor. We're driving this with some input voltage as a function of time. We determine the magnitude and phase responses of this circuit. First, we transform the circuit into the frequency domain. So the capacitor's impedance was 1 over j omega c. Once I substituted the appropriate capacitance, this impedance became 4 over j omega. Keep in mind that this is now a function of omega. we're going to be able to put in a signal with any frequency here and determine the output associated with that input. The resistor's impedance doesn't change. It's still 2 ohms. It's independent of frequency. This turned into a voltage divider in the frequency domain. Once we did that analysis, we determined that the magnitude response was 2 over the square root of 4 plus omega squared, and the phase response is the negative of the arctan of omega over 2. Now at this point I want to do another example of calculating a frequency response. So I've got an RC circuit frequency response that I did previously, so now I'm going to do a frequency response of an RL circuit. I have a 2 Henry inductor. In series with a 1 ohm resistor, I'm applying a source voltage across the terminals of those two devices. I'm measuring my output as the voltage across the inductor. My input is V sub S of t, of course. Now, since I'm interested in the magnitude and phase responses, it's implied that I want the steady state sinusoidal response of this system. Therefore, we're going to be working in the frequency domain. So we can transform this circuit to the frequency domain. The input voltage gets converted to a phasor. We have not specified the frequency of this phasor. That's important. The output voltage is also specified as a phasor, which we do not know its frequency until we tell it the frequency of the input. We do know that the output phasor will have the same frequency as whatever this guy does. The resistor's impedance just transfers directly over, so it has a 1 ohm impedance in the frequency domain. The inductor's impedance is J times omega times L. That becomes J times L is 2 Henries. Omega is still an independent variable. We've now got a representation of the circuit in the frequency domain as a function of frequency. This now, again, looks like a simple voltage divider. So my output voltage phasor is this impedance over the sum of these impedance times my input voltage phasor. So V as a phasor is V sub S as a phasor times this impedance, which is J2 omega, over the sum of these impedances, which is 1 plus J2 omega. Now, from this, I can determine the frequency response, H of J omega. Now, the output is equal to the frequency response times the input, so this is simply my frequency response. So the frequency response is the ratio of the output to the input. That is going to be J2 omega over 1 plus J2 omega. Now I need to determine the magnitude and the phase of this. So the magnitude response, magnitude of H of J omega, is equal to the magnitude of the numerator. This is a purely imaginary number. Its magnitude is just 2 omega, over the magnitude of the denominator. To take the magnitude of a complex number, I take the square root of the square of the real part. 1 squared is just 1, plus the square of the imaginary part, which is 2 omega squared. The phase angle, H of J omega, is the phase angle of the numerator. So J has a 90-degree phase angle. It's pointing straight up along the imaginary axis, which is 90 degrees counterclockwise from the real axis. So the phase angle of the numerator is 90 degrees. I subtract off the phase angle of the denominator, which is the arctan of the imaginary part of the denominator, which is 2 omega, over the real part, which is just 1. So my phase angle is equal to 90 degrees minus the arctan of 2 omega. And I'm done with this example. Okay, now we've had some experience calculating frequency responses. We can determine a magnitude response. We can determine a phase response. However, it is most common to represent magnitude responses and phase responses in graphical form. What we have is one independent variable, frequency. Omega is our independent variable. Since H of J omega is a complex number, you essentially have 2 dependent variables. You have the real part as a function of frequency and the imaginary part as a function of frequency. Now, as I said previously, we represent H of J omega in polar form. That corresponds to 2 independent variables, the magnitude response and the phase response. So I need two plots to fully represent the frequency response. I have to plot the magnitude response versus frequency and the phase response versus frequency. We'll go ahead and do that for our previous two examples on the next couple of slides. Now let's simply create plots of the magnitude response and the phase response for our two previous circuits. I'll do the RC circuit first. We found that our magnitude response was h of j omega is 2 over 4 plus omega squared. If I plot this, it looks something like this. This sort of makes sense. If omega is 0, I have 2 over the square root of 4, which is 2 over 2, which is just a gain of 1 at 0 frequency. As I increase omega, the denominator gets larger and larger. The amplitude goes down. It will eventually decay to an amplitude of 0. Now later on we'll talk about filters and frequency selective circuits. What's happening here is that this circuit is passing through low frequencies. Okay, if I put a very low frequency input into it, the output will see that readily. But extremely high frequencies will be stopped by the circuit. If I put a high frequency input into it, I'll see virtually nothing out. Plotting the phase response. The angle of h of j omega was the arctan, negative of the arctan of omega over 2. If I plot that at low frequencies, when omega is 0, the arctan of 0 is 0. As omega goes to infinity, the arctan of infinity is 90 degrees. This will decay down to minus 90 degrees. Now let's take a look at the same information for the RL circuit that we did. Now let's look at the RL circuit that we did earlier this lecture. Our magnitude response was 2 omega over 1 plus 2 omega squared. If I plot that, it looks like this. Makes sense. As the frequency is 0, the denominator becomes 1, the numerator becomes 0, and my amplitude response is 0. As I increase omega, okay, as omega gets large, this 1 becomes negligible compared to omega squared. I can throw that away. The denominator for large values of omega is going to look like the square root of 2 omega squared. So it just looks like 2 omega. So for big values of omega, this looks like 2 omega over 2 omega, which is just 1. So for high frequencies, my amplitude response is going to approach 1. This is doing, in some sense, the opposite thing that the previous circuit was doing. If I put a low frequency input into this circuit, it's going to be strongly attenuated. You're not going to see much output from a low frequency input. However, if I put a very high frequency input in, it's going to pass that on through and give me a lot of output relative to the magnitude of the input. This is generally termed a high pass type filter. Now, the previous filter was a low pass type filter. This is a high pass type filter. Those are two main categories of circuit response shapes in the frequency domain. That's why these are the two examples that I'm going to continue to come back to throughout this lecture and into the next lecture. The phase response for this, 90 degrees minus the arctan of 2 omega. If I plot that, when omega is 0, this guy becomes 0 and the phase is 90 degrees. As omega goes to infinity, this becomes 90 degrees. 90 minus 90 is 0. The phase will roll off to 0 degrees as omega goes to infinity. So far, we've been primarily concerned with the frequency response of systems, in our case circuits, how the circuit responds to some arbitrary input as a function of frequency. Now, since we're taking a look at systems as a function of frequency, it is helpful to also look at the signals, the inputs and outputs to and from the system as a function of frequency. Now, the frequency domain content of a signal is called the spectrum of the signal. The plural of spectrum is spectra. We're going to be talking about signal spectra for the next couple of slides. For example, if I have some signal v of t, which is 3 cosine of t plus 20 degrees plus 7 cosine of 2t minus 60 degrees, I can represent that in the frequency domain. Now, this guy's going to be discontinuous because I only have components here at frequencies of 1 radian per second and 2 radians per second. So if I write this as a function of frequency, its spectrum will look like it is represented as a phasor as a function of omega. V of j omega has a magnitude of 3 and a phase angle of 20 degrees when omega is 1 radian per second. It has a magnitude of 7 and a phase angle of negative 60 degrees when omega is 2 radians per second. There are no other sinusoids in this signal. The phasor representation is 0 for any other frequency. Now let's take a look at representing this graphically on the next slide. Now, signal spectra are plotted essentially in the same format as our frequency responses. We have a magnitude and we have a phase. They're both functions of frequency. So we're going to end up with amplitude and phase versus frequency. We'll need two plots. For our example, the magnitude of V of j omega as a function of frequency, it's 0 everywhere in here, except for frequencies of 1 radian per second and 2 radians per second. At a frequency of 1 radian per second, we have an amplitude of 3. For a frequency of 2 radians per second, we have a magnitude of 7. These are sometimes called stem plots, line plots, lollipop plots. They're just indicating that this is defined only at certain specific frequencies. The phase response is also defined only at frequencies of 1 radian per second and 2 radians per second. Okay, the magnitude is 0 everywhere else. That actually makes the phase somewhat undefined, except at these 2 points. I don't know exactly what it is because the phase angle is an angle from the real axis. 0 is on the origin. I don't know really what direction 0 is from the real axis angularly. However, at 1 radian per second, we have a phase angle of 20 degrees. At 2 radians per second, we have a phase angle of negative 60 degrees. This is the spectral plot of our previous example signal. Now, since we have a graphical representation of the input as a function of frequency, we have a graphical representation of the system's response as a function of frequency, we can use those plots to get a graphical interpretation of the system's response. Okay? So, plots of the input and the frequency response can be used to provide an output spectrum plot. This can sometimes provide some insight into what's going on. Essentially, you multiply point by point the magnitude plots, right? The magnitude of the output is the magnitude of the input times the magnitude of the frequency response. The phase angle of the output is the phase angle of the input plus the phase angle of the frequency response. So sometimes doing this graphically gives you a better intuitive or physical feel for what's going on than just looking at the equations. So let's take a look at our previous example signal applied to some system and see what the output response would look like graphically. As an example of a graphical interpretation of our output, what I'm going to do is take our previous RL circuit and I'm going to apply that example input that I did on the last slide to it and see what I would expect the output to be from a graphical point of view. Now, here I'm only going to look at the magnitude response because I think that gets my point across well enough. The magnitude of my input forcing function. I did that on the previous slide. It looks like these two non-zero values. Everything else is 0. My frequency response magnitude looks like this. It is defined for every frequency. However, the input magnitude is 0 for any frequency other than 1 radian per second and 2 radians per second. So I really only care about the amplitude response at those two frequencies. So at 1 radian per second, my amplitude is 0.89. At 2 radians per second, it's 0.97. To get the output magnitude, I can multiply these two together. So I'm going to take these two and multiply them, and I'm going to get my response by a frequency by frequency multiplication. Remember, in here, the input amplitude is all 0. So in here, in this frequency range, this curve is multiplied by 0. I get 0 output. Now I have a 3 here at 1 radian per second. I multiply that times this 0.89 to get 2.67. Again, I have a chunk of frequencies here that have a 0 input. 0 times all this stuff is just 0. My only other non-zero value is at 2 radians per second. I take 7, multiply that by the frequency response at 2 radians per second, which is 0.97. My output is 6.79. The input 0 for any other frequencies, so the output has to be 0 for those frequencies. I can only get outputs out where I put actual frequencies in. If I don't put an input in, I'm not going to get a sinusoidal output out from a linear system anyway. And now I'm starting a slightly new topic. It builds on our previous topics, but it's a little bit different way of looking at things. We're going to be thinking about frequency selective circuits and filters. We're going to be thinking in terms of the shape of the frequency response of the circuit. As we saw in the previous slide, if we take our input magnitude and multiply that by the circuit's magnitude response, we get our output magnitude. Okay, so the circuit's magnitude response gives us some idea of what shaping will be done by the circuit on the input in order to get the output. So circuits are often characterized by the general shape of their magnitude response, since that shape is essentially applied to the input spectrum shape in order to get the output spectrum shape. So the response at some frequency ranges typically will be high relative to the input. We say that those frequencies are passed. Previously, when I was looking at our RC circuit and our RL circuit, we saw that the RC circuit had a strong response to low frequencies. It was passing low frequencies. The RL circuit had a strong response to high frequencies. It was passing high frequencies. In general, the magnitude of h of j omega is large where frequencies are passed. And at the moment, I'm not sure what large means. Okay, essentially, large means relative to the magnitude response at other frequencies. Now, the response in some frequency ranges also will be low relative to the input. These frequencies are said to be stopped. For our RC circuit, high frequencies were essentially stopped because the magnitude response of the circuit at high frequencies was low. For the RL circuit, low frequencies were stopped. The magnitude response of the RL circuit at low frequencies was small. So the magnitude response is small relative to where it's large, really, in the frequency ranges where the input is said to be stopped. Okay, now I want to introduce a little bit more nomenclature relative to filters, which are synonymous with frequency selective circuits. As I said before, circuits have frequency ranges where they pass signals and frequency ranges where they stop signals. So circuits which select certain frequency ranges to pass and other frequency ranges to stop are often called frequency selective circuits because they're selecting particular frequencies, or more commonly filters. They're filtering out some frequencies. For example, if you have a graphic equalizer on your audio system, you can adjust the gain in various frequency ranges to tailor the sound to how you like to hear it. Okay, you can increase the bass. Okay, you're going to start passing more bass signal through. You can increase the treble. You can pass more treble signal through. So you're essentially creating a little filter when you're adjusting your graphic equalizer knobs or sliders. So a couple of nomenclature things. The range, or typically called the band of frequencies that are passed, is called, for obvious reasons, the pass band. The range of frequencies or band that is stopped is called the stop band. So when you're talking about filters, people will usually talk about the pass band and the stop band. In this course, I'm really only going to talk about two types of filters, low-pass filters and high-pass filters. I'm going to talk about low-pass filters first. Low-pass filters pass low frequencies, as the name would imply. They, by implication, stop high frequencies. So an ideal, okay, emphasis on ideal, low-pass filter has some pass band where it passes through any inputs and some stop band where it stops any inputs completely. So whatever frequency I apply in the pass band goes straight through. If I apply an input in the stop band frequency, I get nothing out. Okay? Since the pass band is at the low frequency end, this is a low-pass filter. Now, the frequency omega c denotes the boundary between the pass band and the stop band. It is typically called the cutoff frequency. So low frequencies are low relative to omega c, or the cutoff frequencies, high frequencies, are greater than omega c. So when you specify omega c for a low pass filter, you've typically specified the pass band and the stop band. Omega c is generally picked to be a frequency that's what you want it to be. Now, one comment. This ideal filter, it lets everything in the pass band through. It completely eliminates anything in the stop band. I can't create this filter physically. I cannot wire up a circuit that will do this process. This is ideal. I can't get this boundary between the pass band and the stop band to be perfectly sharp. In order to do this, I would need a circuit which responded to some input before I applied the input. It would need to be able to see into the future to do this. So this is idealized. Later on we'll talk about non-ideal filters. Now let's talk briefly about high-pass filters. As the name implies, high-pass filters pass high frequencies and stop low frequencies. Graphically, their amplitude response looks like this. High frequencies are within the pass band. If I put a signal in that's in the pass band, I get a lot of output. Low frequencies are now in the stop band. If I put a signal into this ideal high-pass filter in the stop band, I get nothing whatsoever out. Again, omega c, the cutoff frequency, is still the boundary between the pass band and the stop band. Okay, we've really just flipped this figure over between the previous slide and now. Now, I mentioned earlier that in this course we're only really going to be worried about low-pass and high-pass filters. There are other filter types, however. I want to mention some of the terminology used relative to those types of filters. Filters are often categorized by the order of the differential equation governing the circuit. Remember when we were analyzing time domain circuits, we did first order circuits, we did second order circuits, and we briefly did higher order circuits using state variable models. The same kind of classification is appropriate for filters. If I have a first order filter, that means that the circuit is first order. If I have a second order filter, that means that I have two energy storage elements in the filter. It's second order differential equation governing it. In addition to low-pass and high-pass filters, other common filters are band-pass filters and band-stop filters. Essentially what these do is they have two cutoff frequencies. So if you look at the frequency response of, say, a band-pass filter, you'll have an omega C1 and an omega C2. It will stop things outside of that band, and it will pass everything through within that band. Likewise, with band stop filters, you pass everything outside of the range between these two frequencies and stop the stuff between the two frequencies. Now, low-pass and high-pass filters can be first order or they can be higher order. Band pass and band stop filters, these guys here have to be at least second order. Now, in this course, I only want to work with first order filters. So all of my filters will be governed by a first order differential equation. They will contain a single energy storage element. With that particular topography, I cannot create a band pass or band stop filter. I need two energy storage elements to do that. That is why I'm not going to touch on these types of filters really at all in this class, other than to mention that they exist. Now let's take a look again at our previous two circuit examples in terms of filters. Our first example was this RC circuit. I had a 0.25 farad capacitor in series with a 2 ohm resistor. That counts as a low-pass filter. When I plotted the amplitude response, it was high at low frequencies and low at high frequencies. So our pass band is down here at low frequencies. Our stop band is up here at high frequencies. This looks like a low-pass filter. Now, This is a real filter that I can build. It does not have a sharp transition between the pass band and the stop band. There is typically what is called a transition region. Now, we will pick rather arbitrarily in a couple of slides the boundary between the pass band and the stop band. At the moment, we're just taking a look and saying, well, at pretty low frequencies, it's passing signals. At pretty high frequencies, it's stopping signals. It looks like a low-pass filter. Our second example is our old RL circuit. I have a 2 Henry inductor with a 1 ohm resistor. When I analyzed this and plotted the magnitude response, I got this. We mentioned earlier that low frequencies are attenuated by this circuit, so this down here is the stop band somewhere, and high frequencies are the pass band. Since we're passing high frequencies, this looks like a high-pass filter. Again, we need to look a little bit closer at where we actually think the stop band stops and where the pass band starts. Now let's talk a little bit more about non-ideal filters and what we want to define as the cutoff frequency for a non-ideal filter. So realizable filters, by which I mean a filter that I can actually build a circuit that will implement that function, don't have sharp transitions between the pass band and the stop band. So you have this little transition region that's neither really passing nor stopping signals, they're just attenuated to some degree. So where do we put that cutoff frequency, omega sub c? Well, rather arbitrarily, what people do is define the cutoff frequency to be the frequency at which the magnitude response is 1 over the square root of 2 times the maximum magnitude that is in the magnitude response of the system. This is rather arbitrary, but it does have a reason why people do it. In general, we think in terms of doing spectrums of signals like voltages. Power would be proportional to the square of voltage. So we think of the power in a signal as being the signal squared. So if you square 1 over square root 2, you get 1/2. So if you're looking in terms of power in versus power out, at this frequency, the power out at that frequency is 1/2 of the power that you're providing at that frequency. That's where people put the rather arbitrary dividing line between the stop band and the pass band. And in fact, sometimes you see the cutoff frequency referred to as the half power point or the half power frequency. Sometimes it's called the corner frequency. Sometimes it's called the 3 dB frequency for reasons that we'll see in the next lecture. It has a lot of names. Generally, things that have a lot of names are pretty important. Remember this stuff, please. Now let's calculate cutoff frequencies for the 2 circuits we've been looking at during this lecture. For our RC circuit, our magnitude response was this. So the maximum magnitude response, so h of j omega max, we said that this is its largest value when omega is 0, and it decreases for higher values of omega. So when omega is equal to 0, we have 2 over the square root of 4, which is just 1. So when the magnitude of h of j omega is equal to h of j omega max times 1 over square root of 2, that's where our corner frequency or our cutoff frequency will be. So if we plot our amplitude response as a function of frequency, and we go to the point where the magnitude is 1 over square root of 2 times 1, which is 0.707 approximately, and follow that down, we get an omega c of 2 radians per second. Now, generally, it's not determined from a graph. It's done exactly the opposite. What you will do is look at this, set magnitude of h of j omega equal to 1 over square root of 2, which is 2 over the square root of 4 plus omega sub c squared. So when omega c squared is 4, this will be 1 over root 2, so omega sub c is the square root of 4, which is 2 radians per second, which is where our cutoff frequency is on the plot. For our RL circuit, our magnitude response is 2 omega over the square root of 1 plus 2 omega quantity squared. As we noted previously, this guy is 0 when omega is equal to 0 because this becomes 0 over 1, and it gets larger as frequency increases. And in fact, magnitude of h of j omega max is when omega goes to infinity. This becomes negligible. We have 2 omega over the square root of the quantity of 2 omega squared. That becomes 2 omega over 2 omega, which is just 1. So we're looking for magnitude of h of j omega at omega sub c is this 1 times 1 over square root of 2, which is 1 over root 2. Now, if we look at where this frequency response becomes 1 over root 2, so magnitude of h of j omega is equal to 1 over square root of 2, that becomes 2 omega over the square root of 1 plus 2 omega sub c squared. Remember, omega sub c is the value of omega that makes this quantity 1 over root 2. I need for this term here to be 1, so omega sub c is equal to 0.5 radians per second. Graphically, what we'll have is our previous magnitude response. Here at 0.5 radians per second, our magnitude response value is 1 over square root of 2 times the maximum value that we see anywhere in this frequency range, which is 1. So if we go to the magnitude of 0.707, follow that across and down, that will be our cutoff frequency. This concludes lecture 29. In this lecture, we've again covered a lot of ground. We started out with our frequency responses that we were calculating before, but now we're starting to emphasize graphing them and trying to get some intuitive feeling for what the frequency responses are doing rather than just calculating numbers or looking at an equation. In the next lecture, we'll continue that trend, keep looking at things graphically, and in fact, we'll start adding some more tools, graphical tools called Bode plots, which allow us to sketch the frequency response rather easily without having to calculate it numerically.